So notice that the red graph is still the one that passes through the point of -1. That's your parent function. I made the value of a be 2, and it's the green graph. So that graph moved away from that 0.11. It stretched. It actually, what happened was it stretched taller. You can see that the same x value, I was at 1, 1. Now I'm still at 1, but my y value is now 2. My y value got multiplied by 2 because why? The a is an outside number. A's change the y values by a multiplier. Notice that the curve is also very symmetrical. If I pass through the point 1, 2, I'm also going to pass through the point 2, 1. That makes it really easy to do your curve. The same would be true if I changed a to 3. Why is it so hard to get to 3? I'm stuck, of course. Of course, it's frozen. Okay, I finally got a to move to 3, and you see it used to be at 1, 1. Now it's at 1, 3. Again, why? The y value, the a changes the y value. So you take your y value, which was a 1, you multiply it times 3, and now you find out it's at 1, 3. Well, if it's at 1, 3, it's also over here at 3, 1. And the same thing is happening on the negative side, okay? It was at -1, -1, but this one is now at -1, -3, and at -3, -1. So that's a nice feature about the parent function when it comes to graphing. Okay, so we were originally considering A is 2 and B was 2. We saw that A caused a vertical stretch. The graph got taller. B, when B is 2, it's going to cause a horizontal compression. What happened with B right here, it changed the x value. The x value was 1, 1. Now the x value is 0.5 or 1/2, 1. Why? Because the b changes the x values. We multiplied that x value, which was 1. We multiplied it by 1 over b, which is 1/2. The b causes, when b is 2, we get a horizontal compression. Again, notice that if this point right here is passing through the point 1/2, 1, it's also going to pass through the point 1, 1/2. And the same thing is true on the negative side. There's -1 at -1/2 and -1/2 at -1. So again, that's A and B do opposite things. When A is greater than 1, it stretches. When B is greater than 1, it compresses. All right, so we've got that written down. So what happens when A is a fraction? So when A is a fraction, you get a vertical compression by a factor of A, and when B is a fraction, you get a horizontal stretch by a factor of 1 over B. Same that we did, same transformation description that we used with square roots and cube roots. Here's what an example of having an A that's a fraction would look like. Here's what an example of having a B with a fraction would look like. We're going to jump over to Desmos and see the vertical compression and the horizontal stretch. Okay, real quick edit. I think I wrote down 1/3 to begin with right here. I'm going to change it to 1/2 just because 1/2 is easier to find on my sliding scale than the 1/3 is, because 1/3 is a repeating decimal. So I did change this to 1/2. Flip back over here to Desmos. I have changed the A to be 1/2. Okay, I'll turn this one off so we can only look at one at a time. The parent function is in red and it passes through the point 1, 1, -1, -1. We changed the A to 1/2, and what happened to it? It did a vertical compression. It got shorter. So right here where it was 1, 1, it is now at 1, it's only at 1/2. Okay, it compressed. It got closer to the x-axis. And again, if it's going to pass through the point 1, comma 1/2, then it's also going to pass through the point 1/2, comma 1. So you can see that right there. And the same is true, of course, on the negative side. We've got the -1 at -1/2, and we've got -1/2 passing through -1. Okay, so for Pete's sake, there it is. Okay, so that's the A. When A is a fraction, we have a vertical compression. And you can see if I get closer to 0, I'm getting really, really close to the x-axis. As I get closer to 1, it approaches the parent function. Okay, and of course the same thing is true on the negative side. If I have negative, a fraction, the negative causes the reflection and the fraction causes the compression. Okay, so that's when A is 1/2. All right, so I'm going to turn A off and let's turn B on. Notice I've got B set to be 1/2. When B is a 1/2, we all of a sudden have a horizontal stretch. We stretched it horizontally. It was at 1/1. We've stretched it out to 2 because our multiplier, remember, is the reciprocal of B. Since B is 1/2, the reciprocal of 1/2 is 2. So the point 1/1 becomes the point 2/1. We change the x values by doubling it. Okay, so it causes a horizontal stretch. Same thing happens down here on the negative side. It has a horizontal stretch. It moved further away from the y-axis. It pulls away from the y-axis. Now, the thing that I want you to see, here's what I think is very interesting. When B is 1/2, compare that to when A is 2. Let's see what happens. We've got B at 1/2, and let's turn A at 2 on. We can't see it, can we? Why do you think we cannot see it? It's right there. So A being 2 looks exactly like B being 1/2. What's up with that? Well, let's go back over here and look at our notes. When A is a number, we get a vertical stretch. When A is a number greater than 1, we had A was 2. And when B was a fraction, we got a horizontal stretch. And much like with the reflection, you can't tell the difference between the horizontal and the vertical because the graph is symmetrical about the y=x line. So you can't tell the difference between a vertical stretch and a horizontal stretch. So a stretch is a stretch. The B, when B is a number that's bigger than 1, we get a horizontal compression. That's the same thing that happens when A is a fraction. So we have an algebra explanation for that, and it goes back to this one right here. So this is when this is our A value right here, and this is our parent function. So when you multiply our A times our 1 over x, we can simplify that. Why? Because we can multiply that. And what happens when you multiply? We're supposed to multiply top times top, bottom times bottom. Well, when we simplify that, that ends up looking like, whoops, I don't know where that A come from. It ends up looking like top times top, 1 times 1 is 1, 2 times x is 2x. So what started off as A is a 1/2, and it ended up looking like B = 2. So that's why when A is a fraction, you get a vertical compression. That looks the same thing as when B is a 2, you get a horizontal compression. So those two, you can't tell the difference between them. Same thing is happening over here with this one. What happens when you divide 1 divided by, where'd my thing go? Oh, did it freeze? I lost my pen. There it is. 1 divided by 2. No, I'm sorry. 1 divided by 1/2. Isn't that what that says? 1 divided by 1/2. What'd you learn in middle school? You keep, change, flip. You keep the one the same. You change the divide into multiply, and then you flip that upside down. So doesn't this simplify to be let's just do 1 over x so that we don't lose the x. We do 1 over x divided by 1/2. So we have keep, change, flip, and we end up with that being 2 on top and x on bottom. 2 on top and x on bottom. Doesn't that now look just like this example that we did over here? Yes, it does. And that's because when my b is a fraction, you get a horizontal stretch that matches my vertical stretch. So it has, when b is a fraction, it's the same thing as when having an a that's greater than 1.